In this video, we're going to investigate the fundamental theorem of calculus. This is obviously an important, some might say fundamental theorem in calculus. And the idea is that it's going to formally connect the idea of derivative with the idea of an integral and show the relationship between them. So this is the piece that connects all of differential calculus, which we've been doing all semester, for all of integral calculus, which we've started in the past week or so, and will continue with going forward and on into calculus 2 as well. So I want to start by considering a function that looks like this. So let's look at the following. So consider the function which is going to be of the independent variable x that looks like the following. So here's my f of x. I'm going to define this function to be the integral. In fact, let's call it g instead of f. I'll save f. So I'm going to call it g of x. And I'm going to have it be the integral of some f of t dt from a to x. So this is where the x dependence comes into play. If you'll remember, when we do one of these integrals with definite bounds, this variable right here is just a dummy variable. So it's gonna wash out of the calculations. It's not gonna show up in the final answer. What will show up in the final answer are the values related to these two things, the endpoints of our interval. And in this case, I've made one of them a variable. We can move this upper endpoint of the interval that we're interested in. So this is the idea. We've got this function where our f of t is continuous on some interval. Let's make it from a to b, and x is also going to be somewhere in that interval from a to b. The function g depends on x, again, and not t. Because t is a dummy variable. This is the word that we'll use for it. We could have used any letter we wanted in there. S, T, Y, some other symbol, some Greek letter, it doesn't really matter. The idea is it is something that doesn't show up in the final answer because only the bounds wind up affecting the final answer. It's just sort of a placeholder. So it's a dummy variable or placeholder until the bounds of integration are plugged in. Okay, so in this case, if you think of x being fixed, so let's write it this way. If x were fixed, so if it played the same role as just a constant, then g of x would also just be a constant because we just plug in some constant here, and this whole thing just equals some number. Hypothetically, it's some specific value. But if x is a variable that's free to move, so if x is able to vary, let's just say if x varies, hence the name variable. So a variable. In this case, g of x is a function And if you pick a different value of x, you'll spit out a different number g of x. That's exactly what a function does. And so that's what we're doing. We're allowing x to move around. So we're letting x move around, which means that the integral, the area that we're interested, is going to vary as well. The area under the curve, and the function that defines our curve is f, so the curve of f, between our starting point A and our ending point x, which is allowed to move around, that area will vary. So g is basically this area. So g is this area. Okay, so hopefully this is kind of clear. All we're doing is saying, here's some function, here's some starting point A, so this function is our f, there's our y, here's our hypothetical t-axis, because f is, remember, a function of t, and x is some point that can move. It's an endpoint. Maybe x is over here, or maybe it's over this way, or maybe it's over this way. This point is allowed to move when x is right here at this point. This is the area that we're interested in. But if x were to move over here, now this is the area that we're interested in. And if x were to move over here, then this is the area that we're interested in. And so as we move x around, the area is going to change. And that area is our g of x. The area will depend on where we put that x. That's all we're saying. So let's do an example, and we can kind of go through this and get a more detailed sense of how this actually is going to work. So let me give you a function that looks like the following. I'm going to draw a picture of our f of t, and we'll figure out what we think the g of x winds up looking like. So let me see if I can draw this semi-carefully. So here is my t-axis, here is y, and I'm going to try to mark this off semi-carefully again. And I want to go up to t equals 6. So let's do 1, 2, 3, 4, 5, 6. I want to go to at least there. Okay, so my function is going to start at this point and go down to there, and then it's going to go straight line to there, and then I'm going to have it go flat horizontally a little bit, and then I'm going to have it do a curve where it kind of curves up through here and then over to there. So this is my f of t function. And let me just label these again: 1, 2, 3, 4, 5, and 6. There's a height of 1, 2, -1. Okay, so this is my f of t. I want to figure out what does the corresponding g of x look like. So the idea is I'm going to let x move around, and we're going to look at the areas under the curve to figure out what the values of g should be. So here's going to be the other graph. I'll have it over here. Make that a little straighter. So this is going to be x and y. And this is going to be the graph of, again, g that I'm going to draw over here. So let me put some points over here: 1, 2, 3, 4, 5, and 6. So we're going to the same 6. 1, 2, 3, 4, 5, and 6. This will be positive 1, negative 1. We'll probably need to go down here a little bit more. I don't think we'll need to go up here, but we'll see. Something like this. And for sake of argument, let's just say, hypothetically, we can go all the way down to negative 3. Let's get all of the points in here. Okay, so what I want to think about is, I'm going to draw over here on the left graph, I'm going to draw some different locations for where x could show up. And I'm going to start with x being right here at the origin, if that is x. And I'm letting a be 0. So what I want to do over here is I want to let my g of x, let me write it down, my g of x is going to be the integral from 0 up to x of f of t dt. It is the area under this curve, my curve f, from 0 up to wherever I happen to put x. So when x is at 0, I'm doing the integral from 0 to 0. What is the width of my region? I mean, it doesn't even matter what the height is at this point. If the width is 0, the total area under the curve is 0. And that means that I'm going to have, starting here, I'm just going to be starting at, let me do it in the same color. I'm starting at the origin here. What is meant to be represented over here is the area. So let me write these down below and we can kind of keep track. Let me put this right there so we can still see it all. Here's the idea. So I want to figure out what g of 0 is. G of 0 is going to be the area under f from x equals 0 to x equals 0. I'm trying to find the area under this curve over here from this point to itself. When x is 0, right, that's all I'm plugging in here. When x is 0, I'm doing the integral from 0 to 0. That is going to be 0, and that's how I plotted this point. That's why I put it at a height of 0 here. When the x coordinate was 0, the y coordinate for the g of x was also 0. So now I want to talk about the next point. This will make more sense maybe. So I want to figure out what g of 1 is. G of 1, maybe I can do it in a different color here, is going to be where x is sitting at that point in blue. So I'm moving x to be sitting at the point 1. And so now I'm looking at the integral from 0 to 1. Up here, what I'm trying to find is the integral from 0 to 1 of f of t dt. I'm trying to find the area from this point to this point. I'm trying to find that area. And the way that I've drawn it, that's just a triangle. It has a height of 2 and a width of 1. And it's a triangle. That total area is going to be 1/2 base times height. So the base is 1, the height is 2, 1 times 2 gives me 2, and it's 1/2 the base times height, so it's half of that 2. This is the area under f, again, from x equals 0 to x equals 1. And that's the area of a triangle that I've drawn in blue there, with base 1 and height equals 2. So what is that total area? It is 1. And I will plot over here 1. There's what g of 1 looks like, right? So g of 1 is the area that we've just found right here. So now I want to take a look at g of 2. So let's do this one in green. So now I'm going up to this point, and I need to look at the collective area from here, so including all this portion that we just did in blue a minute ago, as well as this new area that is now going to be negative because it's underneath underneath the x, or in this case, sorry, the t axis here. So I need to look at the combined area of this region plus this region. We just found the area of this region. It was 1 because it's a triangle with a base of 1, a height of 2. This one is an area of a half because it's also a triangle with, in this case, a base of 1 and a height of 1, but it's downward, so it's negative. And then I multiply that by a half. So 1 times -1 times a half. And I've got to add those two pieces up. So again, this is I'm going to stop writing this after this one, area under f from, in this case, x equals 0 to x equals 2. And so I need to subtract basically the 1 that we found before, which was the area of that first blue triangle, and now I need to subtract off the area of that little triangle. So minus the area, area of the triangle with a base of 1 and the height of -1. So this means that this whole area is a 1/2. I've already taken the minus sign into account there. So 1 minus that half leaves me with a half, and so that means that my next value should be here at a height of, roughly speaking, that would be about a half. So let me delete those, but that's where I got that point. Oops. Okay, so there's my first 3 points. We're going to just kind of go through this now continuously. I'm going to stop doing everything so color-coded. So I want to figure out what g of 3 is now. G of 3, again, is going to be another area. But now I'm interested in the area from here all the way up to this point. So I've got the 1 that we found for this triangle minus a half that we found for this. So these two pieces combine to be a positive 1/2, a positive 1 minus a 1/2. So positive 1/2. And to that, now I'm adding the area of this little square under here. And it is a square with an area of 1, and it is negative because it, again, is below the t-axis. So those two regions combine to be the 1/2 that we just found. All I need to do now is subtract 1 from that, and that'll give me a -1/2. So it'll give me the area that we had before. Let me write this. The previous value was a half, and I'm subtracting a 1 from that because I'm subtracting the area of this little, do another color. Why not? I need to subtract the area of basically this region. So that's the region that I'm subtracting off. And that's what gave me this 1 right here. So 1/2 minus that 1 gives me a -1/2. And so that's what I will come back and draw the height of my curve as over here. -1/2 at 3, that's right about there-ish. Doing it again, let's do orange now. Here's the next region that I'll take into account so that I can get all the way up to g of 4. Let me scooch up a bit here. So I'm going to take the -1/2, which is the area that we were just sitting at. That's where I'm getting that number. So I'm going to take that -1/2, and then I'm going to subtract an additional 1 from that because, again, that's the area of that new orange region that I just added. And that will give me -3/2. And that's what we would plot right here. There is, I guess I should do it in my orange again. There we go. There's -3/2. And just continue on this way. The next point, I'm going to add whatever this weird shape is. I'm not going to try to do this exactly. Let's just see if we can ballpark that. It's definitely not quite a full square, so it's not quite another -1. It's not the same as this triangle here. That would need a straight line right there. Because it's not a straight line, I know it's going to be more than -1/2, or I guess rather less than -1/2, but not quite -1. So somewhere between. So let's just, for sake of ease, let's call it -3/4 maybe-ish, ballpark. So I don't know. To get to, here we go. g of 5 will be at the negative 3/2 that we were at, and then subtract whatever that area of that purple region is, which is maybe minus, I don't know, let's just say 0.7. Close enough. I'm just, again, guessing, ballpark. And so that would put me at what? Negative 1.5 minus 0.7. That's like negative 2.2-ish. Oh, come on. There we go. Negative 2.2. Draw that in purple. Negative 2.2. We're sitting somewhere down here. And then to get all the way to g of 6, we'll be at this negative 2.2. And I will now add back, what color have I not done here? Let's do light blue. That's nice. I'm going to add back that area, which is an exact mirror image of the purple area that we just added, but it's now positive instead of negative because it's above the t-axis. So I'm going to say that that's the exact same as adding that 0.07 back, which will put me back to negative 1.5, or the negative 3/2 we had before. So that should put me right back to this same height as the orange point that we were at before. And then if I just kind of connect the dots and think about how these things are connected, this was going to be a straight line. This will be a straight line. You can see those are all on a straight line there. And then this one, really it should kind of be more rounded because of the shape of the region that we had here. This is a straight line because if you think about how the area increases as I move from the red point to the dark blue point, we're just adding in area in essentially a fairly linear-ish way here. Well, I actually add a little bit more at the beginning and a little bit less at the end. This thing should be actually curved a bit. I probably shouldn't have drawn it as a straight line, I guess, now that I think about it. So it should be something maybe more like that, and this should be something a little more like that. But this is kind of the shape that we wind up with. You can just connect the dots, and we've got an approximation for g of x. And we got it by just finding g of various values, g of 0, g of 1, g of 2, 3, 4, 5, and 6. Plotting those points, and then kind of playing connect the dots a little bit. So this is the idea. This function is the function showing all the different areas under the curve of this particular curve from 0 up to a given x value of our choosing. So we just slowly change the values of x. This is exactly what we just defined way up at the beginning. This is this g of x. We've just picked 0 for our starting point, and we used the particular drawing of f of t that I drew down there. Okay, so g of x is basically this cumulative area under the curve. G of x represents the cumulative area under the curve of, in this case, of f of t. All right, let's zoom in a little bit. Good enough. Okay. Okay. So, I've claimed in the past that what we essentially just did was an integration, and that it is the opposite, the inverse operation of differentiation. So if we take the derivative of this g of x, we should get back the f that was inside of the integral sign. So I want to see if integration, which is what we just did, and differentiation are inverse operations, and I don't know why I'm putting this in quotes. They don't need quotes. If they are inverse operations, then, trying to write the word then g prime, when I take the derivative of x, I should get back f. And we won't get the t back necessarily, because as far as the g is concerned, it has no idea that a t ever existed. It is a function of x. When we take the derivative, we should get back some f, but it'll only know that there was ever an x. So we should get f of x. So let's take a look at this. So let's see if this happens. But that is our hope here. Let me just zoom out just a bit, give us a little bit more room. Okay, so let's actually compute this derivative. So I'm going to do it with our limit definition here, just to kind of think about what goes into it. So g prime of x is going to be equal to the limit as h goes to 0 of some g of x plus h minus g of x, whole thing over h. That's our limit definition of a derivative from earlier this semester. Let's just treat h as though it were a small number. So let's just again do an approximation here. So this is basically, for small h, it's really, we can get rid of the limit and get a decent approximation without the limit. So all I'm saying is, let's kind of undo the limit. Now I don't have something that's exact anymore, but it's a decent approximation as long as h is pretty tiny. Okay, so g prime of x involves taking the difference of these two areas, because remember, g represents the cumulative area under the curve. So it represents looking at two different areas, the difference between two areas, and then dividing by h, this tiny number. So let's write this down. G prime of x is represented by, or involves, let's say that, involves taking the difference of two areas that are presumably pretty close together, then dividing by h, where h is essentially going to be a width in this case. Okay, so if I just take the expression that we had a minute ago, and I take that g prime of x is approximately equal to g of x plus h minus g of x, the whole thing divided by h. Algebraically, I can just multiply both sides by h, and I will get that h times g prime of x should be approximately g of x plus h minus g of x. Algebraically, this is not a very scary thing. All we've done is multiplied both sides of this thing by h. But now I want to take this expression that we've got over here on the right, and I want to give a geometric interpretation of that. So I want to go back to our picture. I want to draw a picture of what we've got going on here. So let's try to visualize this and see if this relationship makes some sense. So, get enough so we can see what we're doing here. Okay, so let me draw the graph that I'm interested in. We'll go this way. We'll go this way. Here is some function, the original function, whatever it happens to look like. Let's just say this is that y equals f of t from before. And here's our t-axis, here's our y-axis. Again, I mentioned a minute ago, this guy will have no idea that t is even in this problem, so in a minute we won't care about this t. And the way that we defined it, we have some starting point, and here's maybe where a point x is, right here, and maybe right here is the point x plus h, a short distance over. So let me draw these two lines in and think about, let's just have our starting point be 0, so let's assume that we're doing the integral from 0. So let's let g of x be, as we did before, the integral from 0 up to x of f of t dt, just like we did in that last example. So I can start here. What that means is that this area right here, this first area up to that point, that area is g of x. You need to zoom in and try this again. Okay, that area is g of x. There, goes a little better. So the area that I've just drawn in is g of x because it is the area under the curve, right? That's what this integral means, from 0 up to x. From 0 up to x. There is my g of x. This area from here over to here, so if I now include this additional piece, that is g of x plus h. And what is this region right here? Well, that's going to be the larger area, which is g of x plus h minus g of x. So g of x plus h minus g of x is this region here. All I did was take the larger area, which is the area from 0 up to x plus h, and subtract the smaller area, which was the area from 0 just up to x. And this distance, just to remind you, between x and x plus h, hopefully it's obvious, that's a distance of h. Okay, so this is what we're looking at right now. What is that area approximately equal to? The area of that region in red is approximately equal to a rectangle with a height of f of x and a width of h. So basically, if I just drew in the edge of the rectangle like that, I can say that, writing this down here, the area of, in this case, that red region, which was, again, oops, I guess I do need those parentheses, g of x plus h minus g of x, that area, is approximately the same as a rectangle with a height, using the left endpoint of that thing, a height of f of x, right? This height right here that point right there is at a height of f of x, right? It's evaluating the function y equals f of t at the point where t is equal to, so the t-axis is equal to x right there. So that height right there is f of x. So it's the rectangle with the height of f of x and width of h. So what I'm claiming is h times f of x is approximately g of x plus h minus g of x. And according to what we wrote earlier, if I zoom out a little bit, after doing the algebra up here, what is g of x plus h minus g of x also approximately equal to? Well, it's approximately equal to h times g prime of x. So algebraically, we found a relationship between g prime of x times h being this g of x plus h minus g of x. And now geometrically we found it to be roughly the area of this rectangle, which is h times f of x. So this is approximately equal, from the algebra before, to h times g prime of x. And so what have we found here? Looking at those two different interpretations, we have that h times f of x, here on the left, is approximately equal to h times g prime of x. And if you cancel the h's, what we find is that f of x is approximately the same as g prime of x. If we actually take the limit as h goes to 0, it turns out these approximations become exact. So in the limit that h goes to 0, the approximation becomes exact. So the point of this is to show what in a minute we're going to call the fundamental theorem of calculus, that basically thinking of g of x as being the result of this integration, finding this total area under the curve, if we then take the derivative of that g of x, we wind up getting something algebraically that is equivalent to geometrically what we have down here. And it gives us a connecting both the algebra and the geometric pictures. We find two different expressions for this little area between basically x and x plus h, this little tiny area. We have two representations for it. We have that it's roughly the area of this rectangle, which is h times f of x, but it's also, due to the algebra up here on the limit definition of a derivative, it's also approximately equal to the derivative times h. And that's what the relationship is that we have here, those two pieces, and it gives us that indeed you take the derivative of this thing that was an integral and you get back the original function f. So this is the idea of the fundamental theorem of calculus. This is why it works. So let me write it down, and we can start to formally see what this thing's going to look like. Okay. There we go. Good enough. Okay, so we're going to write this fundamental theorem of calculus down in two separate parts. Here's the first part. Fundamental theorem of calculus part 1. And then we'll do part 2 in a minute. Okay. Here's all the buildup that we need, but again, we're just expressing the idea that we've already kind of fleshed out. So if f is a continuous function on that interval, so continuous on some function, on some interval from a to b, let's say, then the function g defined by the following. So g of x being the integral from some point a up to x of f of t dt, where again this endpoint x needs to be somewhere on the interval where this function's continuous, where f is continuous. We can't have this point be in a region of this function f where suddenly the function's doing weird stuff and isn't well behaved, or it's not continuous. But this function g, defined by using this integration symbol, is also going to be continuous. So it turns out that g is also continuous on AB, and it's differentiable, at least up to the endpoints. So indifferentiable on the open interval AB, where we're excluding those endpoints. And the most important part, g prime of x equals f of x. This is the thing that we just figured out a minute ago. So this is the fundamental theorem of calculus, part 1. And again, I'm going to just put this up here. Oftentimes in short, you'll just see this abbreviated FTC, and we'll call it 1 for part 1. Fundamental theorem of calculus, part 1. So this is basically what we just showed long ways in the previous example. Essentially, if you define g to be the integral of f, then you take the derivative of g and you get back the original f. With essentially what it's saying, how we're going to use this in practice is, if I want to take the derivative of something that looks like this integral, all you need to do is basically take whatever's sitting up here and plug it into this function, and then ignore everything else. Get rid of the differential, get rid of this piece. This is just going to be f of x if I take the derivative of this whole piece. Just plug whatever variables up here down into that. We'll see, it's a little more subtle than that, but we'll see examples down the line. So let me write down the fundamental theorem of calculus part 2, and then I can show you some of the ways in which these things will kind of get used. So, oh, not yellow. Don't want to highlight. Let's see. All right. Fundamental theorem of calculus part 2. Which again, we can abbreviate as FTC2. Okay, what this one says is the following. If f is continuous, so we have this same function f, and it's continuous on AB, then the following is true. The integral from a to b of f of x dx is going to be equal to f of a, sorry, doing this wrong here, got these mixed up, let me undo that, f of b minus f of a, where this capital F that I've suddenly introduced is the antiderivative. Antiderivative of lowercase f. So basically f prime, capital F prime equals lowercase f. That's the idea. And we actually used this before in the video for section 5.2, where we basically found an antiderivative and evaluated it at these two endpoints. So I kind of jumped the gun and showed you how we were going to use this. That last example in section 5.2 was basically an application of this fundamental theorem of calculus part 2. This is what we did. We'll do a bunch more examples of this. You will get more comfortable with this. I should mention just real quickly, if you're looking at the PDF of my notes, I just caught a typo in here. I have that it's equal to f of a minus f of b, and that would only be if I'd switched these two things around. So this is the way that it is correct. This is the correct way of writing everything. It is in the PDF of my notes. If you're looking at that, this is mixed up. So, okay. Essentially, this also kind of just refers to the example that we did. It's kind of a different interpretation. It's saying that if we just add up all the stuff between A and B, so all the F between A and B, we can actually evaluate that total area by simply observing another function, this capital F, which is the antiderivative of the lowercase f, at these two single points. So if you think back to the problem that we did at the beginning, Let me just go back up and reference this one, the rainbow colored one here. Okay, this one here. If you think about this function, g of x being kind of the antiderivative of this one, to figure out the total area under the curve, all I needed to do was actually look at the difference between basically here and here. And the total area under the curve between those, I started at 0, and we wound up at, what was this, negative 1.5, I think? Yeah, negative 3/2. This total integral of this function, taking into account all these little pieces that we're adding up in between, I can evaluate it by simply just looking at this point here, and taking the difference between them. And it'll take into account the net effect of all of the little pieces of area that we added up over here with all the colors. I'm just going to take those 2 points, find their difference, so negative 3/2 minus 0, negative 3/2, and this winds up being the integral from 0 all the way up to 6 of this function. So that's kind of the idea here. If we can find what this function is, it turns out it's the antiderivative. So, okay. This thing kind of seems weird other than the fact that we did it in this example, but we're saying that we're somehow taking this function and adding up a bunch of areas related to this function, and instead of doing all of that, I can just evaluate this different function that's related to this one just at 2 single points, as long as this capital F is the antiderivative of this lowercase f. So I want to give you an example that will maybe put this into a little bit more context and give you a little bit more intuition for why this might make sense. So let's talk about position, velocity, and acceleration, because we've done that before. So let's stick with, for now, velocity. Let's let v of t be velocity. So I tell you what the velocity is at a given point in time. Remember, the velocity is the derivative of position, right? So, which we might write as x of t. So what I'm saying is, when you take d dt of x of t, we get v of t out of it. That's what we're claiming. What that means is, if I were to look at this, if we look at the following expression, I want to take the integral from a to b of v of t dt. I want to figure out what this represents, and it makes more sense if you think about this now in terms of the quantities we're dealing with now. It's not necessarily areas under a curve, but related to this idea of velocity position. This, we just said, is velocity. So this has position, it has units of some sort of length per time, distance over time. So let me write that, distance over time. What is this? Well, that's the differential, and you can see it's dt. It's a little tiny piece of time. So this is tiny, that's what the d indicates, but the t indicates that it also has units of time. It's just units of time. And so when I multiply a velocity times a little bit of time, right? Essentially what I'm saying is we've kind of got our d equals RT formula, our dirt formula. If I take a rate, which is what this velocity is, and I multiply it by time, I get back a distance. If this time happens to be a really small amount of time, I'm just seeing how far did we travel in a really small amount of time, but it's going to be a small distance. So this is the idea. I'm taking whatever our velocity is. This is not necessarily tiny. The velocity could be very large. I'm tracking for a very small amount of time, multiplying these together, and I'm seeing basically how far did we go in this small interval of time. But the result is a distance. So when I multiply these together, I get a distance. What does this piece say I need to do? I need to add up. This is a big sum, basically. Our integral sign stands for an S, stands for a sum. I'm summing up a bunch of these tiny distances to get one big distance. This tells me at what time I should be starting. So this is my start time. Oh, really can't write. Start time. B is my end time. And again, this symbol just means sum everything up. So all we're doing is, in this case, summing a bunch of tiny distances. So this whole thing, we are going to sum a bunch of tiny distances to get a larger distance. And when we talk about distance, distance is a position. What mile marker, so to speak, are we at? Distance and position are interchangeable concepts in this case. So, taking one more step back. So these are kind of the technical details that go into this. But big picture, all we're doing is I'm going to track the velocity. So if we simply track the velocity from t equals a until t equals b, so from some start time to some end time, we can figure out, based on how much time has elapsed and what were the velocities in between, we can figure out our total distance. It's going to be simply x evaluated at b minus x evaluated at a, which is our total distance. Okay, so let me clean this up a little bit to just make sure this makes sense, because this is a simultaneously profound idea, but also a very intuitive one, because most of us have driven a car before. There are two different ways to think about how far I've traveled. Here's the technical way of how we've been doing it. We track our velocity, right? If we track velocity starting at time A all the way until time equals b, and I keep track of what the velocity is for every single instant of time in between. Maybe part of it we're going on the highway at some constant high velocity. Maybe we drive into town, go off an exit ramp, and we have to stop at a stoplight. Our velocity goes to 0 for a while. Then we accelerate up to city driving speed, 35 miles an hour. If we keep track of this velocity throughout this entire time, we can add up all these little tiny distances. So just keep track of what was our velocity for this 1 second interval of time. And for that 1 second, we were going 60 miles an hour, and you can figure out how far you must have traveled in that 1 second. And then do it for the next second, and the next second, and the next second. And we'll get all of these little tiny distances that we will add up together to get a big total distance. Or I can just give you the position function, tell you what position we wound up at, position at time B, what position we started at, position at time A, and if I look at the difference, I'll know how far I went. So if I just tell you we started in Albuquerque, we ended in Santa Fe, I can tell you the total distance. Time 0, I was here. Time 1 hour, I was at this other location. Here's how far we must have gone. And I can do that by just looking at the position function. And how is the position function related to the velocity function? It is the antiderivative. So what I'm saying is the integral from a to b of v of t dt is simply going to be equal to x of b minus x of a. This is a total distance traveled. And this is also the total distance traveled by just looking at the difference of our starting and ending positions. There's two different ways to think about how we can come up with that total distance, by keeping track at each instant in time of all these little distances and adding them up, or just saying, okay, I have this position function. I know where I started. I know where I ended. Let me just take the difference between those, and I can find the total distance. And the idea is, in this case, x of t is the antiderivative of v of t. Right? If v of t is the derivative of x of t, then x of t is the antiderivative of v of t. And that's the relationship between the v here and the x here. This is exactly what the second part of the fundamental theorem of calculus tells us. This is the exact same expression, just now written in terms of velocities. Okay, hopefully this makes sense. This is the computer keeping track of your speedometer at every instant in time, and then just adding up, multiplying it by however long has elapsed, times that velocity to get a little tiny distance, adding up all these little tiny distances to get a big total distance. And here is a big picture. Here was our starting position on our GPS. Here is our ending position on our GPS. This is the total distance that we must have traveled. And to be fair, you would have to take into GPS is not a good example because we're turning and stuff, and it's not a straight line distance. We're just saying here's the starting position, the end position, here's our total distance traveled. Okay, hopefully that kind of makes sense. Hopefully I didn't obscure it more with that example. But let me just do a few quick examples, and then I want to show you at the end maybe kind of a slightly different way of writing the fundamental theorem of calculus 1 and 2 that will be ways that will be relevant, that will show up down the line. So you may not see them in quite the format that I wrote them up there, but you may see them in slightly different but equivalent formats. Okay, so let's just do some examples to just get comfortable with this concept. Practically speaking, if I want to compute the integral from 0 to 1 of x squared dx, I just want to find out what this is. What I'm claiming is, if I can just find the antiderivative of x squared, I can just evaluate it at this point and this point and take the difference. So that's what we're going to do. What is the antiderivative of x squared? Well, I know it's going to be something x cubed. When I take the derivative of x cubed, I'll get 3x squared. I don't want 3x squared. I only want 1x squared. So how do I take into account that 3? I need to undo it with a factor of a third. So 1/3 x cubed is the antiderivative of x squared. If I were to do the plus c here, so again, we did this before. Let's say hypothetically we do the plus c. And I'm now going to evaluate it. This is my vertical line that just means evaluate between the points 1 and 0. What this means is I will plug in 1/3 times 1 cubed plus c. There's this function evaluated at the upper limit. And then I will subtract off the same function evaluated at the lower limit. 1/3 times 0 cubed plus c. And what do we get out of this? Well, this first term, the 1 cubed is still just going to be 1. I'll take a third of that, and I'll just get a 1/3, plus this c. Evaluating 1 had no bearing on the c. And then for the second piece, I will subtract off, plugging in a 0 here. 0 cubed is still 0, so a third times 0 is still 0. But this minus sign will distribute through, so I will have minus 0, and I will have minus c. And this will cancel. I have a plus c and a negative c. They will cancel, and I'll just be left with 1/3. This part where the c's cancel will always happen when we have a definite integral, because we will be evaluating at the two endpoints, and both endpoints will involve a plus c. So I'll have a plus c here, a plus c here, and when I take the difference, they will cancel. So in general, we do not include this. Don't even bother. Only on definite integrals where these endpoints are numbers. In the next section, section 5.4, we'll start talking about something called an indefinite integral, where I remove these bounds, and the plus c will be important again in those cases. But as long as I'm evaluating our function between these 2 points, you can think of the plus c showing up in both places. It'll always cancel. So going forward, I'm not even going to bother to write that plus c anymore. So let's do another example. I want the integral from 2 to 4 of e to the 2x dx. So again, we just need to figure out what the antiderivative of e to the 2x is. I know it's going to be something that involves e to the 2x. If I take the derivative of e to the 2x, I will get back e to the 2x, right? E to the stuff, so to speak. What's the derivative of e to the stuff? E to the stuff, so another e to the 2x, times the derivative of the stuff. When I take that derivative, I'll get a factor of 2 here. But I don't have that factor of 2 here. I don't want a factor of 2. So how do I undo that factor of 2? With a factor of 1/2. This is the antiderivative. 1/2 e to the 2x is the antiderivative of e to the 2x. This is how I do them. I think about them as pairs. Integration is hard, and you're going to find this out both in this class and then definitely in calculus 2. Integration is a lot harder than differentiation. So whenever possible, frame it as a differentiation problem. I know that when I take the derivative of e to the 2x, I'm going to get back into e to the 2x with some modification. So I know the antiderivative is going to involve the e to the 2x. Now let me just think about what it would look like if I took that derivative. And when I take that derivative, I'll pick up an unwanted factor of 2. There is no factor of 2 here. I'll have one if I took the derivative of e to the 2x. And so this 1/2 will account for that unwanted factor of 2. It'll cancel it out for me. This is my process for all of these types of problems. And lastly, we simply take that and evaluate it between the two endpoints, from 2 to 4. And so plugging in, I will get 1/2 e to the 2 times 4. There's my upper bound. And from that, I'll subtract off the lower bound, 1/2 e to the 2 times 2. And if we look at this, both of them have a factor of 1/2. This is going to be a power of 8. This is going to be a power of 4. And I'm just going to write this as a 1/2 times e to the 8th minus e to the 4th. Leave it like that. That's our final answer. You can evaluate these in a calculator and come up with a decimal approximation of this, but this answer is exact. This is the final exact answer to this problem. Let me do one more, and this will highlight one other issue. So I'm going to do the integral from -1 to 2 of 1 over x squared dx. Okay, let me just move this down over there. Perfect. Okay, so I can think of this piece right here, my integrand, as x to the -2 if I want. And that maybe will be easier to deal with when we do the antiderivative. So what is the antiderivative of x to the -2? Well, it must be 1 power higher, so it must be x to the -1. When I take the derivative of x to the -1, the power will indeed drop to -2, but this power will come down and become a coefficient in front, and I'll pick up a negative sign that I don't want. I'll get an unwanted negative sign. So to account for that, I'll put another negative sign to cancel it out. So this is the antiderivative of x to the -2. And all we're doing is evaluating it between -1 and 2. And so when I plug in these values, the first one will be -2 to the -1 power. Right? So there's plugging in the upper bound. From that, I will subtract off plugging in the lower bound. I'll get -1 to the -1. So I'm just plugging in the +2 in place of x here, and I'm plugging in the -1 in place of x on the bottom. So let's think about what this gives me. The 2 to the -1 power, that just means that this is the same as a 1/2, and the negative sign just persists. So this is just going to be -1/2. For the other piece, I'm going to have 1 over a -1. But this negative sign will cancel with that negative sign, so it'll be 1 over +1, which is just the same as 1. And then I'm subtracting that, so 1 additional minus sign. So we've got 3 minus signs here. Triple negative, which stays negative. We've got a -1 here. And what do we get out of this? negative 3/2. So negative 1/2 minus 1 is negative 3/2. So that's our answer, right? The answer in this case is no. That answer is wrong. And let's think about why it's obvious that that answer is wrong if we draw a picture. I want to think about what the graph of this looks like, 1 over x squared. No matter if I plug in a positive or a negative value for x, this ratio, 1 over x squared, because it's getting squared, it's going to be positive. So if you actually look at the graph of this thing, it looks like, so here's my x, here's my y, you wind up getting a graph that actually looks like this. It's kind of like a hyperbola, but it's positive on both sides. Whether I pick a positive value for the x here, I'm squaring it, and 1 over a positive number is going to be positive. And if x is negative, I'm also squaring it, and I'll have 1 over a positive number and get a positive number here. So it's symmetric in both ways. And we're saying all we're doing is taking the integral from negative 1 up to 2. So this is the area that we have just supposedly tried to find. It cannot possibly be negative. So we got an answer, and our answer is wrong. Why doesn't this work? Well, if you look at the graph, it's kind of obvious. We have an asymptote right here. Our function isn't continuous. So why doesn't this work? We're violating the requirements of the fundamental theorem of calculus. Let me go way back up to it real quickly here. So here's what we were trying to do. But it requires what about this function? F needs to be continuous on the entire interval that we're going to be evaluating on. So the whole area that we're going to be finding, our function needs to be continuous. And our function is not continuous. It has an asymptote. So the fundamental theorem of calculus doesn't apply. Not all the conditions are met. So it doesn't work because 1 over x squared is discontinuous at x equals 0. There's an asymptote. So it's not continuous on, doesn't matter that it's at 0 so much as that it's not continuous on the interval from negative 1 to 2. Any point in there where we had some discontinuity could throw this off. So fundamental theorem of calculus part 2 doesn't apply. You'll talk about dealing with problems like this in calculus 2. And essentially what you're going to have to do is break this into 2 separate integrals. One everywhere to the left of the discontinuity, one everywhere to the right of the discontinuity, and take the limit as this endpoint approaches the discontinuity and add those 2 chunks together. And you would wind up getting a positive result in that particular case. So for us, as far as we're concerned right now, this integral does not exist. And you'll learn how to try to deal with cases like this in calculus 2. So we find it's a type of what's called an improper integral. So, but for now we find that the integral from negative 1 to 2 of 1 over x squared dx does not exist. Okay, so this should give you a sense of kind of everything that we're looking at, kind of the big ideas behind it, and in practice this is going to be important. You're going to need to be able to do this type of a problem. Recognizing the relationship between a function and its antiderivative and just evaluating that antiderivative at these 2 points. This is the big idea of the fundamental theorem of calculus. Just 2 quick alternate formulations that are going to be important just because you may see these. So alternate formulations of the FTCs, the fundamental theorems of calculus. So they may not always be quite the wording that we have up here, so assume all those same requirements are in place, but we can reframe the fundamental theorem of calculus part 1 into the following. We can basically just say, if you take the derivative of the integral from a to x of some f of t dt, whatever that t is, it doesn't matter, that's our dummy variable, all we do is get back f of x. So this is an alternate formulation. It's saying we're taking the derivative of the integral. This derivative is going to undo this integral. What's important though is that this number, this value here, winds up going into in place of the t. It takes the place of the dummy variable. This whole thing, remember, this is what we were calling like our g of x. It's just a function of x. At the end of the day, this thing is going to be a function of x. And when we take a derivative of it with respect to x, we should get another function with respect to x. T is just a dummy variable. So just keep that in mind. A second version of the fundamental theorem of calculus part 2 can also be done kind of in a similar way. If I say the integral from a to b and make it totally explicit, f prime of x dx, so I'm building the derivative into the integrand. So I'm taking the derivative of the antiderivative. It's equal to f of b minus f of a. So essentially, again, same thing. We're undoing the operation. Here I'm taking a derivative, but here I'm taking the integral of that derivative. What happens? The integral and the derivatives wind up canceling, and we get back just something that involves the same f. Here's f prime, but I'm integrating. The prime and the integral sign cancel, and we wind up just dealing with f, now evaluated at those two endpoints. So hopefully these kind of both make sense. We take the derivative of the integral of some function f, and we get back something that only involves that function of x, or sorry, of f. And same thing here, capital F, I'm taking the derivative of it, then taking the integral. I should get back something where those undo each other, and we just wind up with something that involves just that capital F. So this is the idea that really kind of hopefully hammers home the point. Integration and differentiation are inverse operations. Okay, so we're almost there. I just want to show you one other quick example. Whoa. There we go. I want to show you one other quick example of applying, in particular, this formulation of the fundamental theorem of calculus part 1, because it's a little bit subtle. What if, for example, you don't just have an x here? What if you have some other expression involving x here, some function of x here? What would you do in that particular case? So in just a minute, I want to do an example of that. So let's look at an example of applying this. And I'm going to actually start with a kind of a tricky example, just so we can see of how to apply. Again, the one I'm wanting to apply here is a different application of this fundamental theorem of calculus 1. I want to use this idea right here. So, for example, what if I tell you that I've defined some function h of x, and that function h of x looks like, let's say it's the integral from sine of x up to 1 of the square root of 1 plus t squared. In fact, let's make this, I'm going to actually change it just a little bit. We do 1 minus t squared dt. and we want to know what is h prime of x. Okay, so looking at this, I've defined a function, h of x, that involves an integral. So t is our dummy variable. We're taking the integral of this expression, plugging in these endpoints, and that's why the final answer will involve this x. And now I'm asking, what is the derivative of this function that involves an integral? And we should expect it should be something like this. I'm going to take the derivative of something that involves an integral, and they should do some sort of cancellation, and we should get a result that just involves this function sitting here in the middle. But it's going to be a little bit more complicated in this case. So let me do, you know what, I'm going to do just a quick side note over here because maybe this would be a better way to do it. Let me do a really quick, easy example first, and then we'll come back to this one that's going to be hard. So let me just do an easy one. What if I just had, same idea, h of x equals the integral from 1 to x of whatever, e to the t dt, and I wanted you to find h prime of x. Well, this one's really easy. We can apply this fundamental theorem of calculus directly. All I'm doing is taking, so h prime of x is going to be d dx of the integral from 1 to x of e to the t dt. The integral and the derivative undo each other, and all that happens is this piece is going to go plug in for that, and we just wind up getting e to the x out of this. That's literally what this fundamental theorem of calculus says up here. If we originally had some f of t sitting in here, and we apply both an integral and derivative to it with respect to this variable x, all that you wind up with is the same function sitting here, but now it depends on x instead of t. So that's what we had. We started with e of t, we wound up with e of x after we applied both an integral and a derivative. Okay, so back to the hard problem. Over here, this isn't quite line up with this. For one thing, these are in different positions. Here, the one that depended on x was on the top, not on the bottom. And here it was just x, whereas this one has sine of x. So I need to deal with both of those things. And this example is going to show you how to deal with both of those things. So the first thing I'm going to do is I'm going to rewrite h of x in the correct order. The integral from 1 at the denominator. So the integral from 1, oh come on, don't fail me now. There we go, 1 to sine of x. And whenever I switch the order, you'll remember this was a discussion we had at the beginning of the video. If this is going from, if this one's going from left to right, this one is going from right to left, and that introduces a minus sign. So if we switch the bounds of integration, we also have to flip the sign of the whole thing. And now I have 1 minus t squared dt. Okay, so now I've taken care of the fact that the term involving the x was in the wrong place. Now it is in the top, just like this example, but it's still not x. It's instead sine of x. So I want to think about what this h prime of x is that we're going to compute. When I compute h prime of x, what I'm asking for is dh dx. But I want to get a variable. I know how to deal with this if there's just a single variable up here. So what I'm going to do is introduce a single variable. I'm going to call it u, and I'm going to let u be sine of x. And so now what we've got is that in this case, our h of x is equal to negative the integral from 1 to u of the square root of 1 minus t squared dt, where again, u equals sine of x. But the problem is, it's not immediately clear that this function depends on x just looking at this part. It looks like it depends on u. And so I want to use chain rule here to rewrite my h prime of x, which again was dh dx, but I've now introduced an intermediate function that gives me a relationship. And I'm going to rewrite this using chain rule as dh du dx. So that's just chain rule from before. And this is going to finally give us all the tools we need to complete this problem. So we finally get the following. When I find h prime of x, which is the goal of this problem, h prime of x, it is the derivative with respect to u of h. And h is this mess right here with the u dependence built in. So it's d du of negative the integral from 1 to u of the square root of 1 minus t squared dt. That is just this part. And now I need to multiply that by du dx. Okay, so there's our chain rule. There is this part, which is just this part. Okay. According to the fundamental theorem of calculus, we can deal with this part really easily now. It now looks like, there we go, now looks exactly like what we've got here, but instead of having an x in these two places, we have a u in those two places, and never mind this minus sign. We can always pull that out. So all this is saying is I'm taking the derivative of an integral, they're going to undo each other, I'm just going to wind up with this function, the integrand of the integral, with a u swapped in place of the t. And we'll have to account for that minus sign as well. So the part in red is just going to become, oops, the part in red just becomes, there's our negative sign, and it's going to just be the square root of 1 minus u squared. And I still have to deal with this du dx. Well, what is du dx? So this piece I need to figure out from the way that we defined u of x way up here. If u is sine of x, then what does this mean du dx is? I just need to take the derivative of this expression with respect to x, both sides. Du dx is equal to, what's the derivative of sine? Cosine. And so that du dx, that's just a cosine of x. So I'm going to take that piece and plug it in place of here. I'm going to take this piece, plug it in back in place of where the u is here, and what we wind up with is that this is negative square root of 1 minus, what was u? U was sine of x. So this is sine squared of x. And what was du dx? That was the derivative, that was cosine of x. So here's what that whole expression looks like. We can simplify this just a little bit. What is 1 minus the sine squared of x? So we can use our Pythagorean identity, sine squared plus cosine squared equals 1, and rearrange that. So we know that sine squared of x plus cosine squared of x equals 1. And if I just subtract this piece from both sides, I'll get that cosine squared of x equals 1 minus the sine squared of x. So that's what I'm applying right here. 1 minus sine squared, that's a cosine squared. So I've got negative square root of cosine squared of x times this additional cosine of x out here. Cosine squared and the square root, those are going to cancel. And we will just wind up with our negative cosine of x times another cosine of x, which is negative cosine squared of x. That's the final answer of this one. This is like the worst case scenario version of this type of a problem. Let me zoom out a little bit. So, just be careful when you're dealing with this fundamental theorem of calculus. It only works nicely if you actually have just the variable x sitting up here and it's in the top. You can just swap it in and these problems are trivial. If instead you have a function of x and say it's in the wrong place, you're going to have to deal with both of those things. You're going to have to introduce this minus sign and change the swap the two bounds of integration. That introduces this minus sign, but then you'll also have to take care of the fact that this isn't just an x, it's now a sine of x. And this will be the procedure. We'll do this substitution. We'll rename whatever this is u, and then we'll use this chain rule right here to solve the problem. So this will be the procedure. It's written out a little more involved than it needs to be. As soon as you see something like this, call this u. Here's our u. Find what du dx is, because we're going to need it in a minute, and then recognize that our chain rule, and we want to find our derivative, is going to be dh du times du dx. So we'll need this derivative for this piece, and dh du, that part can be done in the exact same way that we did this problem over here. That part can be the trivial part, exactly like we're doing here, taking the derivative of an integral, and you just take this bound of integration and plug it on in, just like we see right here. Okay, so hopefully that clears that up and will allow you to do all of these homework problems. And I will try to knock out the next couple of videos and hopefully have them posted within the next 2 days.